Automatic valves or pilot-operated control valves, same thing, tend to intimidate because they look so, with all the tubing and everything, so mysterious. And a lot of people just run shy of them, which I did in the beginning, to be honest. But they're not that bad to understand. Let's take a look at it. Now, a full description would be automatic. They're typically self-regulating standalone valves with no separate controller. They do their thing on their own. You can add external control, but most of them are all by themselves. Pilot operated. Small externally mounted controller pilot the operation just as a pilot controls a plane. Without the valve, or without the piloting, the basic valve is useless. Not even a good anchor. Hydraulic, they're actuated by the water they handle, particularly differences in pressure. An important point. That difference has to be there. Control valves, and they can control water pressure, flow rate, level, other parameters. They're basically still valves. In other words, they can throttle, and that's about the extent of it. Basic components, the typical automatic valve has a body. The flow, in most cases, we'll get into that later, comes from underneath and is throttled by a disc retainer, which has a rubber seat on it that seals when it's closed. Um, what else it has in addition, though, is that throttling disc retainer is tied to a diaphragm or piston in some cases that moves out and up and down. So there is a chamber above that. The other thing to note is in most cases there is a spring in the cover. Why is there a spring in the cover? We'll get to that in a minute. Minute's over. The reason that spring is there is to ensure that there always is some differential between the inlet and the outlet of the valve. Okay, low flow rate head loss. This shows a typical head loss curve, head varying is square flow rate, and you can see it's linear for the different valve sizes, except you've got this hockey puck thing shown on here. What does that mean? That means is if the body is completely open, the valve is completely open, you'll get the straight line from the end to the beginning. If it is using the spring, which it does in most applications, then in fact you do get a beginning head loss in the thing at lower flow rates to the point that there is a minimum head loss that you are unable to go below. Okay, now typically the straight lines are defined by the CV of the valve, and if you've never dealt with CV is a number which effectively defines the head loss characteristics of a valve or just about anything. And you can see the equations. CV is defined by flow velocity divided by square root of pressure, and if you play games with that equation, you can get other factors if you know any of the other two. And the only way to overcome that spring is to vent to atmosphere, which is often impractical, or go dual chamber valves, which vent to atmosphere, but they're essentially closed open valves only. And we'll get into that again later on. Now, let's say we want to learn how these valves operate and they're just way too tricky. Well, here we are, 3 simple lessons. The first thing you will note is the effective area of the diaphragm is effectively about a third or a half more than what the base is. For example, 13 square inches on a 4-inch valve across the seat. The effective area of the diaphragm is about 20, and divide the two of them, you end up with a ratio about 1.5 to 1, which is called the trip ratio. In other words, the diaphragm or piston has to have a larger effective area than what the seat of the valve does. Okay, now assume flow is left to right, inlet pressure of 100 psi and an outlet pressure of 70 for a difference of 30 psi. Looking at it here, our 4-inch valve will have a lump up force of 390 pounds. That's 30 psi difference. It's got 70 psi above it, 100 psi below it. So the seat has 30 pounds trying to open it over an area of 13 square inches. So 390 pounds force is trying to open that valve as we see it right here. But if we run a line from the inlet of the valve to the cover, we now have 100 psi above, 70 psi below over an area of 20 square inches, which means we have 600 pounds forcing down. So with 390 pounds forcing up and 600 forcing down, 210 pounds force will keep the valve closed. Rule number one, inlet pressure to cover will close the valve. Okay? Lesson number two. Sorry about that. If instead we run a tube from the valve cover to the outlet, the diaphragm will no longer produce a downforce because you got 70 pounds below, 70 pounds above, and the 390 pound force we talked about over the seat will cause the valve to open up. So outlet pressure to cover, valve opens. And some valves are literally that simple, like a three-way solenoid valve that will connect either inlet pressure or outlet pressure to the cover. The valve will do its thing. It'll either open when outlet pressures to the cover and close when inlet. Interesting to know that automatic valves will actually work in reverse. Normal waterworks flow is under-over, goes under the seat and then comes over because they throttle better. They don't get what's known as bathtub effect if you go the other direction. But going the other direction, in other words, let's say from right to left, still, if you look at that thing right now, the line to the cover, which when we're going left to right, close the valve, will actually cause the valve to open. We can go through the details of that, we won't. But basically, that over under situation, right to left, will cause the valve to control if it's configured that way. Why would you do something like that? In the petroleum industry, in case the diaphragm or whatever should fail, the valve will fail closed. But in waterworks, not such a risk, so we pilot the way it's normally drawn, left to under, over, okay? Now the third rule, if you got the first two, inlet to cover closes, outlet to cover opens, this is the third and last trick, modulating. Simply means adjusting to provide control. When you drive at a steady speed on a hill or car, you're modulating the gas pedal. The computer does it in cruise control. More gas if you're going up a hill, less as you're going down. Now what we do is we run a line from the inlet to the cover and restrict it. Let's say it's restricted to 5 gallons a minute. Then on the other side, between the cover and the outlet, we have a valve that can outflow that 5 gallons per minute through the orifice on the left-hand side there. So right now, with that closed, there's no flow there. So effectively, you have an inlet to cover at 5 gallons per minute restricted flow, but still an inlet to cover connection, and the valve will close. Now, if we open that valve, that manual valve that we had, completely, and it can flow 10 gallons a minute, then you have 5 gallons a minute from the inlet going to the cover, but 10 gallons a minute going from the cover to the outlet. Effectively, it has an outlet connection, and the valve will open. Again, cover to outlet, open, okay? If we happen to throttle the valve just right, the little manual valve, to 5 gallons a minute, the valve will stay put. What's going into the cover is coming out, and it just stays put. You notice basically that the main valve simply amplifies the action of the pilot device. On those previous illustrations, the pilot device was like a cock, but if you replace it with a direct acting pilot control, which we'll get into more detail, we have a modulating valve. Basically what the pilot does, the main valve will do. All pilot controls are small direct acting devices capable of a water control function at low flow rates. When installed between the cover and outlet of a much larger valve that also has an inlet cover with a restriction, it will cause it to duplicate the same function. What the pilot does, the main valve will do. Okay? And under ANSI AWWE C530-17 states the following basic variations. Pressure reducing function. That by far is the most common. Pressure relief, sustaining, as we get into that, essentially is the same action. That's probably the second most common. Solenoid control functions, pump control function, altitude controlling level in the reservoir control function, and rate of flow. In other words, the valve will limit flow to a given rate. And we'll get into all those functions, okay? First off, pressure reducing function. A pressure reducing pilot, if you look at this thing, uh, basically you have a spring pushing on a diaphragm, but it's connected around to a seat. You see where it says disc? That is connected to right up where the diaphragm and spring are. So when the spring is pushing down on the diaphragm, that disc will be pushed away from where the flow would come down. Therefore, it's open. You can blow in one end of the valve. This valve will come out the other side, okay? And what happens is when you put the thing in line, outlet pressure is pushing on the diaphragm. If the outlet pressure is below what's needed to push that spring up, that thing is open. And since again, it's on between the cover and the outlet, and it can outflow the restriction, the valve will open. If the outlet pressure is high enough and can push with the diaphragm against that spring and cause that disc to rise up and close, then it's closed. You can't blow through it. And if you hook it up to the valve, the big valve, basically speaking, it will be closed because it hasn't got an outlet connection anymore. It has that inlet with the restriction. Therefore, inlet connection, main valve will close. You have an adjustment screw so you can control the force on that spring, compression of the spring, and by that you can set what you want. Go a step further. And we go through the whole thing about diaphragms and force and everything else. If the pilot diaphragm has an area of 2 square inches and the spring force of 200 pounds, when the pilot outlet pressure reaches 100 psi, the disc retainer will start to throttle and control the outlet pressure. You may have a similar device in your house right now. If you have a pressure reducing valve, basically speaking, it is a direct acting pilot. Is same as a direct acting pilot. And in fact, you can swap the two of them. If you take the pilot off a control valve and put it in your house, it'll control pressure and control, in your house. Now, if you take the one in your house and put it on the valve, an automatic valve, it will control the automatic valve. And it can be, 6-inch valve. It will control it. The functions are identical. Now, get into applying sizing. Most important consideration with pressure reducing valves is sizing. Appreciate these are throttling valves, and too big a valve simply cannot control at low flow rates. Consider trying to fill a glass of water from a fire hydrant. A simple rule number 1, that a pressure reducing valve with a 2-inch diameter seat can handle flows right down to 0. Larger valves simply cannot. That is my dictum based on experience and testing. Therefore, if you intend to flow down to 0, and most applications you will, particularly at 3 o'clock in the morning when nobody's drinking water, etc., 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 then your initial valve, your smallest valve, should be no larger than 2-inch. Okay. Now, based on that, and here's the flow rates of what pressure reducing control valves can handle. They can go up to about flow rates of about 25 feet per second quite easily, which means the maximum flow capacity of a typical valve is, and there's the numbers given for different sizes. Any one of these valves can be paralleled with a 2-inch valve to permit flow from 0 to the combined flow. For example, if you've got a 2-inch and a 6-inch valve hooked up in parallel, the little one, the 2-inch, can handle up to about 260 gallon a minute, and you'll have it set a little bit above the 6-inch valve, and it will then take over, and your combined maximum flow, as I say, 2-inch will take you down to 0. Your combined maximum flow, 260 for the 2-inch valve, 2250 for the 6-inch valves, give you a total of 2510 US gallon per minute. Now I've got one shown here, what we're talking about, sort of. You can see the big valve being parallel, and you can see the small valve over on the branch above it. They've pushed it further than I would recommend. They've got a 12-inch valve being controlled by a 2-inch. But I'll tell you what doesn't work, and that's using small direct acting valves, say half, 3/4 inch, with a 6-inch valve, or even up to a 12. It just doesn't fly, okay? Surge pilot. One of the things about pilot controlled pressure reducing valves is that their closing rate is a bit slow because it's simply the water going from the inlet to the cover to close it has to go through an orifice. So if the pressure picks up downstream pressure, the pilot closes, and now it's up to that line going through the orifice, it's going to take it a while to close. So if downstream demand falls off fairly quickly, say somebody shuts off, testing a hydrant and shuts it off, you may find that the flow through the orifice is not enough to get the valve down quick enough, and it does a locking situation where it hasn't come down quick enough. Inlet pressure is outlet pressure, and the only thing that is closing it is the spring. So we've showed it here. Not only overpressure downstream because we've lost control, hot water tank safety valves are going. There's no pressure differential across the valve, therefore no hydraulic closing force, and only the cover spring is closing. And that can take a long, long time. Minutes closing in on an hour, okay? So how do we get around that? The solution is to connect a pressure relief pilot between the inlet and the cover, but with the sensing line connected to the valve outlet. Applied in this manner, pressure relief pilot is called a surge pilot. Same difference, but got a new name. Set just above the normal pressure reducing pilot setting. So if the pressure reducing pilot closes and can't control the closing of the valve and the pressure continues to rise, the surge pilot will then open and very significantly speed up valve closing because it can flow a heck of a lot more than what that orifice can. It also, in an emergency, will act as a bit of a backup pilot. It can't take down to zero, but it has that effect if flow rates are up there. So basically, and we'll get to that in a second. Thumb number 2, all valves 4-inch and larger should really be configured as pressure reducing / surge valves. In other words, have this surge pilot on them. Highly recommended. And it has solved a lot of problems over the years. Now here you can see the piloting. There's the main valve. There's the orifice, which is tied to the inlet. Connection down to the cover. Line carries over. There's the pressure reducing pilot. If it closes, flow will come through the orifice and close the main valve. If the pressure reducing pilot is open because it sees a low pressure, then it will flow more than the orifice and the cover will open because of that outlet connection. But if the flow rate drops off and the pressure gets too high, the pressure reducing pilot closes and the orifice can't close the main valve quick enough, and we're losing our downstream control. The surge pilot sees it, and let's say we're set at 60 psi and the surge pilot set at 70. As soon as it sees 70 pound, it will open, and immediately you've got a line from the inlet up to the surge pilot and straight down into the cover, and it will get that valve. Now, so the moment it drops below the 70 psi, that pilot will close and basically play control. If it has to open a bit, it will. And so it's not a case that you're slamming the valve shut. You're not. You find that all of a sudden, I lost control. I can't maintain 60 because of the flow dropping off. All of a sudden I hit 70, and that's as far as you're going to go, which is what you want. Cavitation. We talked about cavitation before, and it's basically, as we mentioned, cold water boiling. Valves can have that happen. You can have pressure drops in that are significant enough to cause cavitation, and they can damage a valve very quickly, okay? There's a simple equation that can be used to find out if cavitation is going to be an issue or not. The critical cavitation outlet pressure is the inlet pressure divided by 3. For example, if the valve inlet pressure is 210 psi, the cavitation outlet pressure will be 70 psi, okay? If you're below that, so you're going from 210 to say 60 or 50, start worrying about cavitation. If you're above that, say 100 psi, 210 to 100, you shouldn't have a problem, okay? Um, has a little bit of a safety factor in it, but that's what safety factors are. Now, let's look at the second most common application of automatic valves, pressure relief. Basically, the pilot is normally closed. It's a little relief valve of its own. In fact, in some cases, it can be configured to actually be a little relief valve for small applications. Okay. Um, Again, it has a spring and a diaphragm, and it externally senses pressure. And the spring and diaphragm have a seat arrangement that the disc retainer that it forces it closed. Okay. Uh, when the sense pressure rises enough to actually force that diaphragm and spring open a bit, then flow can conduct through, and you'll see in a minute how they're rigged. That causes the valve to open. Okay, and it has adjustment screw just like the others. Let's take a look at how they're piloted. There you can see the pilot down in the bottom left, just slightly over from center, and you can see it has a seat that is connected up to the diaphragm, which is pushed down on the spring. And if you hold the thing in the palm of your hand, it will be closed. Where a pressure reducing pilot is normally open, hold it in your palm of your hand, you can blow through it. This one is normally closed. If you try to blow through it, you can't because it is normally closed. Now, what happens is, if, because again, an area is 2 square inches, spring force of 300 pounds, when outlet pressure reaches that 150-pound setting, the disc retainer will start to open and control the main valve inlet pressure. And you can see it's piloted over there. If it opens, the main valve opens. For, like, let's say normally closed. So we have an inlet pressure that's below 150 psi. The pilot is closed. Therefore, the only connection to the cover is through the orifice or a little needle valve shown here, and that will close the main valve. At 150 psi and above, the pressure, and you can see the sense line that goes back to the inlet, when that inlet pressure gets to 150 psi above, it will start to open that pilot, and as it opens it and exceeds the flow going into the cover, then the main valve will open just as the pilot is opened. Okay? And we go through the whole description of it. Very often, they will, instead of using an orifice, we have this little needle valve shown here. That's because with it, you can kind of control the closing speed. Do you want a lot of flow or little flow in? And it tends to stabilize. You can adjust it and stabilize it out so that the valve doesn't close too quick and cause surges or whatever. Applying a pressure relief / sustaining valves. Why do we call it pressure relief and sustaining? Because it basically is a valve that stays closed until inlet pressure reaches the valve set point. Then it'll open as necessary to control inlet pressure at that setting. That's a pressure relief valve. A pressure sustaining valve is a valve that stays closed until inlet pressure reaches the valve set point. The valve will then open as necessary to control inlet pressure at that setting. In other words, it's the same valve. Really no difference at all. But how it is connected. Like at the bottom left schematic here, you've got a pump connected to system, and you've got a branch. And let's say you don't want the pump to apply more than 150 psi. If, for whatever reason, system man goes down and we hit 150 psi, the relief valve will open and dump 2 atmosphere. In fact, I've heard of going back into the reservoir and using that as a pressure control means for the pump. It will work, but it's not the most efficient way of doing it, let's put it that way. If you take the exact same valve and put it in a line, let's say you've got a pressure zone and you don't want it to drop below a certain point in the lower zone, you can set this thing, let's say again, say 100 psi. Okay, fine. If we're over 100 psi in the upper zone, this valve will open up and everybody's happy. But what happens is if the upper zone pressure drops to 100 psi, this valve will throttle its way down and control that upper pressure at 100 psi. Okay, so it's a pressure sustaining valve. They're the same valve, just how you hook them up. Sizing. Pressure relief valves rarely called upon to operate and typically see a very significant pressure differential between inlet and outlet. Accordingly, are sized to handle flow rates up to about 45 feet per second or more. I've known people who've set them or use them for higher design flow rates as a relief valve. But 45 is a good safe number. But pressure sustaining valve, which is the same valve, except it's flowing all the time in service as a rule, almost all the time. Therefore, you treat it like a pressure reducing valve and design it to maximum flow rates of about 25 feet per second. Now, there is a thing called a surge anticipation valve, which is considered an enhancement of pressure relief valve. They are not related to pressure reducing surge valves. Well, an interesting valve to review. It's a valve that the theory goes that if the pump shuts down quickly, there's a pressure drop, and which will then go up to the reservoir, reflect, and come back, and we want to have the valve open before that pressure comes back. They've caused more problems than they solved. I'm not a big fan of surge anticipation valves. I found that in municipal systems set up properly, a ordinary pressure relief valve can catch that wave as it comes. It's not a fraction of a second shock, it's over several seconds. The valve can keep up with that, and they usually, you do not have a problem, okay? So if you just pretend they don't exist, they won't bite you. You can add pressure relief function to any off-on valve, okay? Solenoid control, altitude valves. Very often, any valve that normally has the ability to close is on-off effectively. If it closes, you can get an overpressure situation in some applications. And a very effective solution to this is to connect a pressure relief pilot as you normally would, sensing line connected to the valve inlet. If pressure gets too high, it'll do its thing. You eventually end up with a valve, let's say an altitude valve, it's hit the level at which you want it to close. It'll close down to and let's say you don't want the inlet pressure to exceed 100 psi. When it sees 100 psi, the valve will start to modulate, and at that 100 psi, close slower, whatever it can, to maintain that 100 psi, and you get a nice smooth closing without any overpressure situations. Now, another on-off function is solenoid, okay? And I'm going to give you a little crash course on solenoid valves. There are two basic types that are used with automatic valves: three-way solenoids and two-way solenoids. Three-way, if you basically want to turn a valve on-off, open and closed, with no other modulating functions, a three-way solenoid simply either connects from inlet to cover and closing the valve, or outlet to cover and opening the valve. Now, a normally open, and again, those three ways come in two versions, and how the hell do you tell the difference between normally open and normally closed three-way solenoid valves? Basically, it's what happens to the pressure port. If the pressure port normally is connected, if you blow in the pressure port and get it coming out the common to the cover, you find that is considered a normally open three-way solenoid valve. When you energize it, it closes the inlet line and vents the cover to the outlet, and the valve will open, okay? That's the action you get with a normally open three-way. If you go to a normally closed, you will find, and that, by the way, is the most common situation. Most people want the main valve, let's say it's 6-inch, to be closed without the solenoid being energized. So in fact, you pick a normally open three-way solenoid, and that inlet line, top left there, which shows down into the cover, means that inlet will go into cover and the main valve will close. If you want to go the opposite direction, where you energize to close it, then you take a look at using a normally closed solenoid, three-way solenoid valve. And normally it connects the cover to outlet, the bottom left corner there, and in doing so, the main valve will be open. So a normally closed three-way solenoid will give you a normally open control valve. And when you energize it, basically connects the cover to inlet and the main valve closes. And if you can figure and understand all that, you're ahead of an awful lot of people that are in the business. Two ways are much simpler. But the only time you use a two-way is when you want to throw in some modulating function as well. For example, I want a pressure reducing valve that pressure reduces when it's energized, and when it's de-energized, it will close. Well, then you put a two-way in series with the pilot so that when it closes, the main valve closes. And if you want it to be when it's slowing down a little bit, if you want the main valve to be open as a pressure or operate as a pressure reducing valve when it's energized, then you will have a normally closed two-way solenoid, and when you energize it, it opens, as you can see here. Um, you pick, okay, energize it, it opens. Normally it's closed, which means if you hold it in your hand, it's closed. Put it in line with the pilot, it's closed, things closed, the main valve is closed. When it opens, when it's energized open, then the main valve will open. And you can get the opposite. You can have a normally open two-way solenoid to get the opposite function, should you so desire. If you want to go a little deeper into solenoid valves, which is worthwhile, I'm going to show it to you here. There are two types of solenoid. Never mind the action. There's also two ways that they are built. Direct and piloted. Now, we've been talking about what the pilots are and what, like direct acting pressure reduced relief valve, which can be direct acting. You can have direct acting solenoids. And basically, as you see in the drawing, this thing is held down. Pressure is such that it forces that little disc down. And as long as the solenoid is not energized, that valve will be closed. When you energize it, it pulls that center core up, which pulls the seat up, and the thing flows. That's direct acting. What the solenoid is telling the thing to do is what it does. Okay? But there's also pilot operated solenoid valves, which are almost like an automatic valve unto themselves. And there's a little hole in the diaphragm, which you can see where it says bleed hole. There's an arrow on the left side of the valve there. It says body, then bleed hole. That bleed hole, which goes from the inlet to the cover, is like the line with an orifice on a control valve, pilot operated control valve or automatic valve, okay? And basically, the flow out of it is controlled by the solenoid. So when that solenoid is closing flow out of the chamber above there, above the diaphragm, then flow will come through the bleed hole and close this valve. When the solenoid opens that chamber, it unloads, again, allows more flow out than is coming in, and this valve will open. So it's like a little automatic valve by itself. Pilot solenoid valves permit higher flow rates. In other words, you can go much bigger. But they are susceptible to fine debris. That little orifice can get clogged real easy. And they require differential pressure to operate. They should not be considered for use when piloting automatic valves. Only use direct acting for piloting purposes. Okay? Little comment on it. ASCO, Automatic Supply Company. Anyway, developed what they call a red hat series of solenoid valves, and they were designed such that the valve body information would be stamped only on a nameplate that was secured under the stem reclaiming clip. The sustaining with that solenoid goes on, it's held in place by that red cap on the top, red hat, okay? And you see under that there's a nameplate. You can see the sort of silver and green stripe. That actually is the nameplate, which tells you what the valve is rated, the size and everything else of the valve. And the coil would have all the basic information stamped on. You see that little bit of blue on the back of the coil, the green thing? That's the information about the coil. So the idea was you could interchange them. You know, if it was the right coil for a half-inch device and it was rated at 120 volt and you wanted it at 240, you just change the coil, pop that cap off, change the green coil, put that same name tag back on because the valve hasn't changed. Boom, and the information will be in the back. Thing of beauty. Except in Canada, CSA, Canadian Standard Association, approves solenoid valves as an assembly, so technically this is not allowed. Certainly it was the intent of the manufacturer, and when I was down in the States, we gleefully did interchange them as things went along. It was just sort of a little hook in the CSA approval. Now, check function. A basic automatic valve can be configured to be a check valve only this is typically added to a valve that has some other prime function. You can have a check valve, and I didn't mention that before. You actually can have a check valve because let's pretend, and I should have gone to the beginning, let's pretend our original slide where we had an inlet to cover connection. Well, if flow is going from the inlet to the outlet, that thing will close. If the pressure changes, in other words, where inlet pressure is lower than discharge, that becomes a cover to outlet pressure, and it will open because you're flowing out of the cover. So basically, that single, as I say, an automatic valve or control valve by itself without piloting is useless. The simplest configuration is simply to add a line from the inlet to the cover. That's it. And one direction from inlet to outlet, inlet being higher than outlet, the thing will close. And if you flip it the other direction where outlet becomes the inlet and it has a higher pressure, the thing will open because it then becomes a downstream connection, okay? And we describe this here to an extent. But the more common thing to do is adding a, by the way, as a check valve, it's not a very good check valve. It closes and it does its thing. But there's far better check valves on the market that are less expensive, better performing, et cetera, et cetera. And we'll get into that in our third station section, okay? So more often when we talk about check, it's something that we add to a valve that is already piloted for something else. For example, here is our standard pressure reducing, okay? Now, we say, well, if the pressure reduces, what's it going to do? Let's take a look at that. Let's say the pilot is set at 100 psi and normally is going high pressure on the left, low pressure on the right, never mind what it says. And there's your orifice and everything else. And if that pilot opens, it's like a cover connection. If it closes, then you've got an inlet cover connection and the valve closes. What happens if the pressure's reversed? The interesting thing is, let's say it's set at 100 psi. If inlet pressure is less than 100 psi, then that will be open. Being open, it will outflow the orifice, and in fact, you have inlet, in other words, right pressure connected to cover, and the valve will close. But if the inlet pressure is above 100 psi, that pilot will close. Realizing pressure reducing pilots are normally open. That pilot will close, and when it does, you're simply left with a cover to outlet connection, and the valve will open. So you really quite don't know what will happen with a standard pressure reducing valve if the pressure's reversed. And you're saying, I don't want that. If they reverse, I want the valve to close. Period. End of discussion. Fine. So here's what we do. We get a nice little check valve, sample shown here, little spring-loaded check valve, okay? And we put low head loss check valve. Put that on the line that goes from the inlet to the cover. Then we run a separate line, and most of these valves are tapped on both sides for pressure source. You could tee it off the other line, whatever. You run from the outlet to the cover through a check valve. Now, if you've got high pressure on the left, never mind what it says, you've got high pressure on the left, flow can go up through that check valve with a little arrow through the restriction, past the cover to the pilot, and if the pilot closes, it will then close the beam valve. If the pilot is open, it will open. Okay, fine. What happens when it reverses? If the pressure reverses, you've got flow through it, this little check valve into the cover from the high pressure sides. Right now, it's going to want to close, and it can't bleed on the other side out of the cover through the orifice and back because there's a check valve in that line, little check valve. So no question at all. Pressure's reverse on this pressure reducing valve, it will close. So it is no longer a pressure reducing valve, it is a pressure reducing / check valve. Okay, isn't that neat? That check feature can be added to almost any valve, and that's basically how it works. Now, we're talking about these valves, some of the accessories, isolation cocks. To permit servicing the valve without having to shut it off online and everything else, quite common to have isolation cocks on every body tapping. They also can be handy if you're diagnosing problems. For example, is the pilot not working? Well, you can take a valve like this, say the outlet side where it goes, you can close it down, see will the main valve close. So always recommended. Uh, Many of the pilot components, these valves are designed to operate with, quote, clean, unquote, water. Particularly the most sensitive thing are needle valves and flow control valves, which we'll get to in a second. They call for a strainer on the inlet supply, typically a flow clean strainer or a small Y-type strainer. A flow clean is literally what they call a needle strainer. Anyway, the finer the mesh, the less chance of the pilot components clogging, but the shorter the time before the strainer itself becomes clogged. When adjustable speed controls are used in turbid water, the best strainer will have a relatively fine screen, somewhere in the 40 to 60 mesh range, with a relatively large area. In other words, a comparatively big strainer if you've got mud is, turbid water is the classic, okay? And that's a subject unto itself, but there's an introduction to that subject. Now, speed controls is simply an adjustable restriction used to slow the operation of automatic valve. Non-modulating valves, in other words, solenoid, power to open, depower to close, very often we'll have a needle valve on each line to control the speed of opening and control the speed of closing, okay? Now, with pressure reducing valves, we mentioned about how you have the orifice is causing it to close and the pilot is causing it to open. Definition of a good operating pressure reducing valve is slow open, fast close. The slow opening because then it's stable, the fast close because if we start to overpressure, will come down. That really is what the surge pilot is doing, is giving you really fast close when you really need it, okay? So one of the things we can do if we want to control the opening but still have the fast close is have a T, and on the line that goes down into the cover, we put in a flow control valve. What is a flow control valve? It is a valve that going one direction, say left to right, the flow comes, just like the one above, comes up under where the needle is, through the needle into what, ever it's set at, and then off to the right. That's the way the needle valve above does. That's the way the flow control. But when the flow reverses the other way, when the pressure differentials the other way, you see that little check valve sort of mounted upside down. That's a little, again, spring-loaded check. And what happens going that direction, you get essentially free flow. It opens and away you go. So restricted, left to right, open, right to left. And put on the cover so the free flow is into the cover, allows you to have control the opening speed, but the closing speed will be as fast as you can possibly get it, which is, you don't want to restrict the closing speed on a pressure reducing valve. You're looking for trouble. Now, position indicator. One of these valves sitting there by itself, you really don't know where the valve is at. Is it open, closed, is it in between? What the heck is it doing? So commonly, you will have a little brass contained glass and a little extension of the shaft that there's a threaded thing on the top left there. There's a thread thing at the bottom that screws onto the top of the shaft of the main valve. So as it goes up and down, the indicator goes up and down, okay? And from that you can see if the valve is full open, when the valve is full closed, or what. Now, what is the difference between the two? If it's not marked, it will always be very close to a quarter of the valve seat size. And there's mathematical reasons why that is, because when a valve is a quarter of its seat size open, the standard poppet valve and automatic valve, the flow area is the same as what an open seat would be. For example, and now we're talking here. For example, if you've got a 6-inch valve, the stroke between open and closed of the shaft will be 1.5 inches. If it's an 8-inch valve, it's 2 inches, etc., etc., okay? Another thing we can do, similar type assembly, but here we've actually got a seal on the shaft and we've got collars that trip a limit switch. So we can actually have an indication if the valve, electronically, if the valve is open or closed or whatever we want. We also can provide an analog device that, and we'll get into controls later on, that will give you a 4 to 20 milliamp signal of where the valve is actually at. Okay? Now I mentioned about combining functions, and Here we show you can have there's a pressure reducing valve. We've added a two-way solenoid directly above the cover. So now it becomes, and the valve will do what, when that solenoid is open, it's a pressure reducing. When it's closed, it is going to close down. So we have just created a pressure reducing solenoid valve moving right along. We can add the check function to that, okay? So there's a solenoid in our pilot, but we've also added the check function on the line that goes to the restriction and one from the cover or from the outlet back to the cover. So now we have a pressure reducing solenoid check valve, which can be and there's infinite combination possible. Rule of thumb number 3, no more than 3 functions, not including check. Check is fairly simple, don't worry about that. But beyond that, you want to have, let's say, pressure reducing solenoid, that's 2 functions, that's fine. In fact, even 3 functions is pushing it. The reason being, the more complex the valve, the more functions it has, the harder it is to understand, the harder it is to service, okay? Now, moving right along, pump control function. If a pump is started across the line, which means it comes up to speed within seconds, okay? You're giving power to the motor instantly, bang, with most pumps, they're very low inertia. They'll come up within 2 seconds, guaranteed the pump is up to speed, okay? Now, what happens is people say, oh, it's the starting of the pump, we've got to reduce the pressure up. Yeah, to a point. But the fact is that when a pump starts, the discharge line has an awful lot of inertia. And although right at the pump it'll come up to shutoff head, that shutoff head accelerating that mass is fairly slow. So usually starting is not the issue. Stopping can be. If the pump is stopped instantly, de-energizing the motor. Now, the motor will not come to an immediate stop. People say you disconnect the power, whatever. The motor comes free float. And we talked about pumps can play turbine running backwards. The motor's along for the ride. In fact, its mass can sometimes slow things down a little bit. But appreciate we can have water flowing backwards through the pipe, in which case then you can have column separation, water hammer. In other words, low system pressure and immediate pump de-energization will cause a drop in line pressure, and we'll get to this more later on, which can cause column separation, where the column actually vacuum forms, water hammer pipe breakage. So that's where a pump control valve becomes a useful feature. Really, it's just an automatic valve with a solenoid function, adjustable speed controls, a check function, and a limit switch. In other words, it isn't that complex a valve. Other functions can be added to it if you want, assuming we're talking a single chamber valve. You need to have the controls set up to be able to do the shutdown. And typically what happens is they're set up such that the solenoid starts the pump to come down, but the pump is set up to keep running as the valve closes. And just before the valve closes, the limit switch, notice above it had a limit switch, the limit switch will then turn off the pump. That's the deal. And on startup, by the way, it is simple. The valve starts moving, the pump starts running. Now, there's a couple of different ways of setting up pump control valves. Set up in line, booster pump control valve is the expression. You can see there's the pump, the left slide. There's the pump pumping through this control valve into a line. Okay, so it's throttling what comes out of the pump. Deep well pump control valve on the side. What it's doing, almost like a relief valve, and in fact you can set them up as a relief valve. You can add that feature as well. Basically, the pump starts, this valve will be open. All the water that comes up is discharged to waste. Therefore, the check valve is closed, and then this valve, which is normally held open, will slowly close, and in doing so, divert flow back onto the main line through the check valve. When it comes time to shut down, pump keeps running. This valve will go back to slowly opening. Therefore, flow is being diverted till the pump becomes useless, hits the limit switch, turn the pump off. That's it. This function can be done using a double chamber valve, which you'll get to, but a less costly is using a single chamber with what they call a spring lift. In other words, the valve is actually opened by a spring to begin with. Instead, the cover spring is taken out and thrown away, and it has a lift assembly on the stem that lifts that valve up. So when it starts seeing pressure, it will start to close, da 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 da, and as it's relieved, it will start to open. That being a single chamber valve also allows you to add the relief pressure option. Now, one thing about these deep well, you have to realize that is not doing the well any favors. The well is surged as fast as the pump can start. The screen around the well and the sand that's packed into it will see very high flow rates because the pump is pumping against, other than the lift of the well. At that particular point, at the pump point, there actually is no other head. It's dumping it to waste. And when we come back out of the cycle and this thing is open, again we're surging. Then we stop the pump and this acts as an air release. Great, except water then goes coming back down the column and surging the screen down below the opposite direction, blowing it out. One could argue that's worse than having the high flow rate to begin with, okay? And here it goes through it. The whole operation of the single chamber valve, everything I've said there, I just said, okay, fine, cool. Solid state starters, which can also have soft stop feature, have eliminated the need for pump control valves and high head, low inertia, fast reacting systems. However, the acceptable motor ramp time is limited. We'll get into soft starts under electric in a bit. And acceptable motor ramping time is limited by heat buildup, roughly half a minute. And therefore, pump control, booster pump control valves still do have some use if they have to be slow, okay? If the action of throttling has to be slow. Adjustable speed drive assemblies, however, unlike solid state starters, can provide virtually unlimited motor ramping and discharge rate. Now, does that mean that variable speed drives, adjustable speed drives should take the place of solid state starters in all cases? No, because an adjustable speed drive, besides costing more, has a built-in automatic efficiency loss of about 5%. And when we get into electrical, we'll see why that is and da-da. Okay, so pump control valve, solid state starter, and adjustable speed drive should generally be adjusted to have a ramp down time that is generally twice as long as the ramp up. Because as I mentioned, starting with a pump is not usually the problem, so half the time is great. It's the shut down that's the problem, okay? Now, altitude control valves. An altitude control valve, basically an open-close valve, non-modulating, that responds to the static head of a reservoir or water tower, whatever. If the reservoir head is less than the desired setting, the three-way pilot will apply low pressure to the cover to open the valve and permit flow. And if the reservoir head gets above the desired setting, the pilot will apply higher pressure to the cover to close the valve. Now, the sensing line should be minimum 3/4 inch and slope upward towards the reservoir. The line that's sensing has to be protected to some extent. You want to keep it from freezing, so that line should somehow be protected from freezing. Not advisable to simply connect the pilot sense port to the valve outlet, as line friction plus valve opening and closing surges will be problematic. This suggests that the altitude valve should be installed reasonably close to the reservoir so we can have our 3/4 inch upward sloping line. A crossfitting should be provided between the pilot and the sense line that is lever operated with a lever operated isolating cock mounted, and we'll go through a description of this whole thing, which I can better show you how it is on here. Here is our sense line. Okay, there's the reservoir, 3/4 inch line. There's the altitude pilot connection. So what we're suggesting is putting a cross in, an isolating cock on the line to the reservoir, an altitude gauge telling you how high the level is in the reservoir, pressure at that point anyway, and a needle valve to bleed. Because one of the things you're going to want to do is set this thing up. And the only way to do it is, unless you can simulate exactly the pressures in the reservoir, without this, is to end up pumping into the reservoir. Oh, I didn't like where it turned off. I'm going to adjust that. Pumping out. Oh, that's not good either. Adjust. You can, and of course, pumping in and out of, or getting water in and out of a reservoir is a production. This thing allows you to do it quite quickly. You run the pump up to operate the altitude valve, filling the reservoir, to the point that you're above what you want. Okay, at that point, close the cock, open the needle valve, bleed down. You're simulating very quickly, simulating loss of level, drop of level in the reservoir. And eventually you'll see the altitude pilot react and open up again, open up the valve again. And you can adjust that. At that point, you can close the needle valve, open the cock, which will raise, and use a bit to throttle, which will raise the level fairly quickly. You can see the point at which it turns off. You can adjust back and forth, back and forth. It turns what can be hours spent setting up the altitude pilot to setting it up in minutes. And here's a spec for the parts that go into it. Historical background. At one time, in place of spring or springs on the altitude valve, which push against the diaphragm, mercury pots were used. Okay, and if you look at the here's the schematic of how they did it. They had one at the top, which would equivalent to the high end, one lower down, equivalent to the lower end. And if you look at the drawing off to the picture, you can see the mercury pots. The bottom ones are about where the guy's hand is. The upper ones are just behind a little chunk of pipe actually running through the trusses. Okay, you can see those two little blue things. Those are the upper pots. Okay, and it explains, it's really nice because 1 foot of mercury equals 13.6 feet of tank head. So the separation between the two of them, if you want 13.6 feet, you put them a foot apart, da 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 da. They were really nice. The issue of having mercury in contact with drinking water, of course, is what killed them. No pun intended. Now, with altitude valves, something that people don't normally tell you, but I'm telling you, beware the 5 and 20 rule, 5 to 20. In very general terms, an altitude pilot control will not fully open with 5 psi or less differential between inlet and outlet. Similarly, the recommended maximum flow rate will be exceeded if the differential pressure between inlet and outlet is 20 psi or more. Okay? In the case of very low differential pressure between inlet and outlet, atmospheric pressure can be used as the low pressure that the valve sees, and it will force it open. It does mean that the pilot circuit opening cover volume valve volume must be directed to a suitable drain to prevent site flooding. So if you aren't draining the opening flow of the cover to waste, then you have to beware that anything less than a 5 psi differential, the valve ain't going to control very well at all. Okay? Similarly, the high end, there are things you can do to prevent cavitation, but if you don't do them, and we talk about anti-cav trim, and we'll get into that in more detail, or have valves in series. If you don't do that, anything over 20 psi differential between inlet and outlet on that valve will cause it, because it's designed to go for full flow, will cause it to go into beyond speeds that it should. Okay? And the risk of cavitation goes with it. Variations. The basic altitude valve can be configured to either close on a pressure reversal or open on a pressure reversal. Two-way flow, one-way flow or two-way flow. In other words, you can use it to pump in and come out of the reservoir, or you can have it only flowing into the reservoir and come back out of the reservoir with a check valve. Now, realizing if your supply pressure is higher than what the tank is, then that check valve will close, okay? It's only designed to allow flow out of the reservoir, not in. That's the advantage of a one-way, is basically that check valve can flow far better than the control valve can if you're needed in a fire. So a decent check valve take the place of having a two-way flow. One-way flow is the way to go. Now, little trick. The difference between opening and closing reservoir levels with the basic pilot set is simply a result of the altitude control function internal of friction. In other words, if you run the reservoir level head to the valve itself, it will open roughly somewhere in the order of, it'll open, but then when it closes, difference between opening and closing about 1 to 3 feet. In other words, if your reservoir is closing at 95 feet, it probably has to drop, anywhere from 94 to 92 to open. And you turn around and say, no, no, I don't want it to be that close. If you can live with it, that's great. It simplifies the piloting of the valve significantly. But if you say, no, 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 I want to have 10 feet between when it closes and when it opens, you can play a little game. And manufacturers provide them, of course. They're into games all the time. Basically what it is your flow line, sense line here. There's reservoir head, and there's the pilot. And there's a little check valve. So as the reservoir goes up, this pilot check valve, and it has to be something, a check valve that has relatively low head loss. Manufacturers need to know that and be good at it. So basically, whatever the reservoir head is goes through the pilot check to the altitude pilot control itself. So in terms of up, no problem at all. But when the reservoir level drops, the pilot check will close, and this differential control device will stay closed as well. So your valve stays closed until you get to a point where the differential across that, and that's what this is, a differential control. The differential across, let's say, is equivalent to 10 feet, which is, what, 4 psi, something like that. Anyway, when it hits that differential, this thing will pop open. As soon as it does, the pilot now sees the much lower reservoir head and immediately opens the main valve. Okay? And there you can see, the bottom, by the way, is the three-way connections, inlet, discharge, and cover. The way the valve is connected, it's a three-way valve, okay? Now, rate of flow control function. A rate of flow control function basically is a modulating differential control pilot, excuse me, that senses the difference in pressure between the upstream and downstream sides of an orifice plate mounted in the flow stream, then modulates the main pilot or control valve to maintain that set orifice plate differential. In other words, it doesn't know flow rate from a hole in the ground. What it's doing is throttling and opening to maintain a constant differential on an orifice plate. And that orifice plate at that fixed differential will have a fixed flow rate. Okay? Each manufacturer has different ranges. Typical rate of flow control pilot is adjustable over an effective pressure range of at least 4 to 1. In other words, 4 psi to 16 psi. That's the range it can adjust. That's the differential across the orifice plate. So if you have an orifice plate that decides to have a 4-pound differential at the desired flow rate, and it's been adjusted to accommodate this, then the flow rate can be increased to about double, because differential varies as the square of flow rate. So if you say, okay, fine, I'm set at 4 psi, I got an orifice plate at 4 psi, you can go up to about 8 psi flow rate through the valve because your pilot will adjust from 4 to 16, but that only doubles the flow rate. So effectively, I screwed that up slightly. 4 to 16 pounds. At 16 psi, the flow rate will have doubled because the head loss varies as the square of the doubling. So 4 times, and there's your 4 times, 4 to 16. Appreciate that overall head loss to the orifice plate also increases, okay? Where it was 4 psi, now it's up to 16 psi. So you've got to have the losses or the capability of doing that. Now, basic automatic valve variations. Sublime and ridiculous. Angle pattern. Basically are nothing but an angle pattern control valve is really nothing but a basic valve, but with an inlet that heads straight at the seat. And you can see in the picture here, it's like an ordinary valve, except the inlet goes straight at the seat, and that's the end of it. They're useful in certain piping configurations, but a couple of comments. Valve 6-inch and larger lumbar angle pattern should not be installed with the shaft horizontal. That is a big thing, since the weight of the internals no longer helps create differential pressure, and a heavy cover spring is definitely necessary. These valves are also difficult to service. I can tell you a story once where a bunch of operators were ready to lunch manufacturers, slaughter, because they didn't appreciate what happens when the valve is mounted sideways, how awkward it is to service. The covers are heavy, and you don't want to bend the shaft. In theory, these valves have a lower head loss, but it's meaningless when differential pressure is necessary to operate the valve. Only a true dual chamber solenoid actuated valve, like the basic pump control valve, we'll get to that in a minute, can take advantage of the lower full open valve loss. Applies to Y pattern valves as well. Now, reduced port valves. Since typical water pipelines are designed for water velocities on the order of 12 to 15 feet per second, and modulating automatic valves can handle flow rates up to about 25 feet per second, a line-size automatic valve is usually an oversized valve, and control problems can result. This is the case people say, well, I want to have a big valve to go. You're looking for trouble. They're flow meters, automatic valves, and I'm trying to think there's a third thing. Too big is too bad. So what the manufacturers started doing a few years ago is rather than saying, okay, fine, where I have a 6-inch valve, we really should put in a 4-inch valve, so put in increasers and reducers to have a 4-inch valve and a 6-inch line, okay? So what we then will do is they started casting bodies that the internals are all identical, okay? The cover and everything else is identical. But on the main valve body itself, instead of, like on the left, having a 6-inch seat, we'll have the guts of a 4-inch valve, okay? Pardon me, the internals will be 4-inch. I lied on that. So instead of 6-inch cover down to a 4-inch cover, 4-inch internals and everything else. We just solved our problem, okay? You've got a valve that you can put in a 6-inch line, but it really is a 4-inch line, and it's much happier because the flow rates are up where they should be. To give you a bit of an example of what happens here, a 3-inch reduced port valve has a 2-inch seat, and at 25 feet per second across that seat, the port flow is 11.4 feet per second, which is typically, you're in what is reasonable design for pipelines. And you can see, let's take a 6-inch valve. 6, we go 2 sizes down because 5 is a stupid size. 6-inch reduced port has 4-inch seat at 25 feet per second. On that seat, again, 11 feet per second at the ports. And because the reduced port valve body has more internal room, the body walls are located further away from the seat and somewhat more cavitation resistant. Let's go back to look at this. If you look at it, when these valves were developed, if you take a look at the valve on the left, the seat is very close to that back wall, okay? So if you've got cavitation vapor bubbles coming out, they're going to strike that wall. No question at all, they're going to strike that wall. But over on the right hand there's a bit of a gap between the seat and the body of the valve. So those bubbles have some distance to collapse. They'll create noise, but they won't have any damage because they're not touching metal, and they're more cavitation resistant. Next variation, dual chamber. Has an inner cover piece situated under the diaphragm and the seat itself, or the poppet itself, okay? So you actually have 2 chambers you can apply pressure to, a cover chamber and an intermediate chamber, inner cover chamber, call it what you want. They're more costly than conventional valves, primarily used for closed opening applications. They can be allowed to go full open as they don't rely on the differential pressure between valve inlet and outlet. You can actually vent them to atmosphere or whatever, and they will do their job. They will simply go full open. It's like a hydraulic cylinder, effectively. They can be most useful in very low pressure applications, where the lower inner cover can be pressurized and depressurized to open or close the valve regardless of line pressure. Where that comes in, water treatment plants. You can put in an automatic pilot-operated control valve, and let's say you're solenoid operating the thing. What you can do is set this thing actually with a spring to force the cover open. You can put a cover spring in that inner chamber so the valve is forced open. Then you can take a source of pressurized water. For example, you've got, say, a domestic drinking system, water system. Take a line off that. And where the main line is seeing maybe only 1 or 2 psi, and you've got, say, 20 psi for the inner cover, and you also run a line, by the way, from the cover itself down to the inlet, or outlet, almost doesn't matter, to the, say, the inlet. What happens is when you apply that 20 psi in that inner cover, it's going to force the valve open. No arguments, it's going to force it open. It'll let, the spring is there to help you do it. Now that was wrong. The cover spring holds it down. I'm sorry, the cover spring is still holding it down. When you apply that inner pressure 20 psi, it'll push up against that spring, forcing the valve open. Flow will go out the chamber connection to the main valve itself. When you depressurize it, then the spring will force the valve back down again. So you can open and close that valve using no pressure other than domestic water pressure, and control flow through the valve even if its pressure is only 1 or 2 psi. Okay? My apologies for screwing that up, but that happens. Piston valves. The original automatic valves, going way back, well over 100 years, were piston valves, and they operate on the same principle as diaphragm valves. Inlet pressure to cover valve closes, outlet pressure to cover valve opens. Main valve duplicates what the pilot does. Now, looking at, they have one advantage over diaphragm valves, but 2 significant disadvantages. Okay? Diaphragm valves tend to roll when the direction changes. If you look at an off-on automatic diaphragm valve and look at the position indicator, you'll find the valve will go about 1/3 of its travel and then seem to stop moving. What it is the diaphragm going from being curved down to curving up, then it picks up from there, and same thing coming back. It'll go down about 1/3, and then as the diaphragm's flipping, the valve actually isn't moving. Piston valves are pure linear. Up and down, away they go. Now, disadvantages. True piston valves are very susceptible to scale deposits on the walls of the cylinder. They will quickly wear out valve piston seal from hard water deposits and often restrict valve motion, making extremely poor relief valves. I remember they were using them in, they didn't know better, in Winnipeg at one time, and one of the city engineers said, we are well aware that most of our relief valves, bigger ones where they're using piston valves, will not open if they see an overpressure situation. They're also more costly to produce. Now Singer came out with the rolling diaphragm valve, originally 10-inch and above, because their 10-inch and above valve was a piston valve to begin with. And then they've converted the 6 and 8 because it's a sales feature that's run away. Uses a bellows ram as a sealing element, derived from a piston, as I mentioned, piston design. It combines the steady movement of a piston valve with the resistance to hard water deposits of a diaphragm valve, but it is more complex, trickier to service. There are diaphragm-only valves, which basically don't have any stem or seat or anything. Well, they have a seat, but they don't have any disc that goes up against that seat. If you look at this thing, you can see this diaphragm is pushing against a seat. Now, the diaphragm itself is sealed off such that there is a chamber created there. And if you look up at the top right, you can see there's a line going. That is equivalent to the cover. And again, we have inlet and outlet tappings. And with that animal, inlet pressure to cover will close it. Outlet pressure to cover, it'll open, and main valve duplicates function. There's several people do that. Roll seal, in-ball, DeRoll. Roll seal, by the way, was bought by Clay, so you will find that type of valve within Clay's catalog, okay? I would consider them only for specialty applications where their size or cost advantages may outweigh their faults. You see them in snowmaking equipment. They're very high pressure valves as a rule. Now, caged valves. This is an interesting thing. Basically, to handle cavitation situations, one of the things that can be done with severe pressure drop, they have a sleeve with holes attached below the seat. It says primary inlet cage, okay? Then above that, you have a secondary outlet cage, which is tied to the disc that's moving up and down. So what happens is the water comes in, goes through the lower set of holes in the primary cage, all the flow converges towards the center. And if it's cavitating, then all those vapor bubbles converge toward the center. They all hit each other, they're noisy, but they don't hurt anything. Similarly, there's a second stage as it tries to come out of that, what they call cavitation recovery chamber. As they try to come out and go out, same thing happens. They have a throttling flow, which tends to dissipate them. But it's really that first one that's doing the action because, yes, the outlet flow was bad. So really, I guess the way of looking at it is most of the action's happening at the bottom there. The holes at the top are really just to help throttle as it goes. They do control cavitation damage. They do have good throttling control, but significant added cost and head loss. That's one of their downsides is they do add head loss. So they're not like a 6-inch valve is, in terms of head loss, equivalent to something smaller. Now, one of the games we can play with these things is go electronic. And we can take a control valve with two solenoids, an open solenoid, a closing valve. The open one, of course, is cover to discharge. The inlet is inlet to cover, okay? And those little bypasses around them are just for testing, that little cock, so you can actually simulate when operating if you don't actually have the power. And those solenoids are activated by a controller, like a PLC, which we'll get into much later. And they can do literally any function you want within reason with that control. So basically, with a preset on-off cycle time, that's how it's normally done. You'll set the time that the solenoid will operate fairly down to several seconds, okay? And let's take a look at how the controller will actually operate. Let's say there's our set point and our pressure's too high. So the controller will energize the closing solenoid, the one on the right, for almost the full cycle time, okay? And of course that has the effect of bringing it down. Now if you just come straight vertical from the end of that action, it looks at it again. No, I'm not quite there. I'm close, but not quite. So again, I'll hit that with a little bit of closing, okay? That brings it down. Now it's going to overshoot. By the time we hit the next time frame, we've overshot and we need to open it. So we'll hit the opening one for a bit of a gap. Not as, okay, start to open it. And again, we're still not there. So a little bit more time. We come up. Oh, I need to come down a little bit. Need to come up a little bit. Eventually it'll average out to the point where the controller, which is sensing pressure through a pressure transducer or whatever, the controller is actually doing the work, the logic, and the valve is simply being told what to do. And at that point, that type of control, and again, we'll get into electronic controls in much more depth. But basically, I didn't, and I apologize, I didn't show you this chart, but I will right now. Okay, as we say, there's your opening time, or pardon me, closing time because we're too high. Then we add a little bit more closing time, we're not there. Again, drawing up from where the next line is. Whoops, we're down, we need to get it open a bit. Again, time, oh, it didn't quite get it, a little more opening. Now we're a little too high, just a little closing. Okay, fine. Touch of opening, pretty soon you're virtually flat. This tie-in with electronics, one of the problems is, of course, with using solenoids like that, is if you have a power failure, the valve, you've got three choices. You can have two, say, normally closed solenoids and have them simply locked. The valve will stay in whatever position it's at. Now, if you're controlling pressure and the pressure rate flow rate drops off, you're going to overpressure the system. Or you can have them fail open, have normally open solenoid valves that you're powering closed when you want, but in a power failure will go open. And at that point, the valve will go open, depending which way the pressures are. And I guess that's really your two options: either lock it in position or have, no, pardon me, you do have choices. You can have the outlet side normally closed, and it'll close, and the valve will close, or you can have the other way around where the inlet side will close and the valve will fail open. So it's basically a case of the valve failing in position, failing closed, failing opening. Whatever it is, it's not going to be a pressure reducing valve anymore. Now, programmable turn-specific motorized rotary pilot actuators. This basic device is programmed to turn the adjusting screw a specific amount in response to an external signal, 4 to 20 standard control signal. We'll get to that later. When fitted to an automatic valve pressure pilot where each turn equates to a set change in pressure, this means that the pilot pressure setting will change in response to that signal. So as you can see here on this illustration, no, you can't see it. We'll come to it in a minute. It basically, a standard pressure reducing valve. You add this device, and with that, you can set the pilot by simply having the control give it a distinct control signal between 4 and 20 milliamp, okay? And if power failure, the thing will simply stay where it's set at, okay? So if it's been controlling at 60 psi, it'll stay controlling at 60 psi. You won't be able to adjust it remotely, but it won't go out of control either. Now, if you've got, let's say, a pump station or valve station where you've got a primary 2-inch pressure reducing, a secondary 6-inch pressure reducing, and the 6-inch, being a 6-inch valve, has a surge pilot on it, to reset those can be a production normally. But if, in this case, we can have it set so the primary PRV, the 2-inch, we can change that setting, and everything else can be programmed to set in proportion. I want the second valve to come on 5 psi below what the initial one is set at, and I want its surge pressure to come on 5 psi above its normal setting. All that can be programmed in. So instead of, oh my God, we got to go out there and set 3 pilots, you can remotely set 1 and the other 2 will come along proportion where they should. Also, the concept of set point offset, increasing outlet pressure with flow rate to compensate for line friction, can easily be incorporated if a flow signal is available. And again, we'll get into that. Now, here's what the system actually looks like. There's a basic pressure reducing valve. You can see the pilot up on the top right of the valve. It's been laid over simply, and there's the device with the pilot on it in the illustration. Starting from the bottom, there's a pressure reducing pilot. There's a little bracket and a coupling that connects it to this motor thing right by the arrow. Above that is just a junction electrical box. And that motor will position so many turns, and you can set it up, so many turns based on the 4 to 20 signal coming in. They're very adjustable, so they can be set for whatever the range of it is, and basically gives you the option of being able to set the pressure you want within the range of the pilot remotely, okay? There we are, done with automatic valves. Hope you enjoyed, and stay tuned for electrical.